Imagine for a second trying to thread a microscopic needle. Like, it takes immense concentration, right? A perfectly steady hand.
Oh, absolutely. It's all about absolute precision.
Right. But now, I want you to imagine trying to do that exact same task, but someone has balanced a 9-pound steel weight directly on the tip of your thumb.
Wow. Yeah, that changes things completely.
It sounds impossible. You have to maintain that delicate precision while actively fighting against this crushing, exhausting physical load. And, well, that paradox is the exact biomechanical reality a medical practitioner faces every single time they perform a specific type of injection.
It really shatters the whole illusion we have of these procedures, because as an observer, you see someone getting a dermal filler and the doctor looks completely calm.
Right. The movements are tiny, deliberate.
Exactly. But underneath their thumb, there is a legitimate high-stakes physics battle taking place. I mean, the forces at play are actually staggering once you run the numbers.
Which is exactly our mission for this deep dive. We are tearing through a massive stack of sources for you today. We've got fluid dynamics models, radiological studies, clinical aesthetic guidelines, even some robotic water jet testing data.
Yeah, the water jet stuff is wild.
It really is. And we're using all of this to decode a highly specific but incredibly important medical engineering challenge. The mission is this. What is the exact extrusion force requirement for injecting thick, high G prime dermal fillers through a tiny 27-gauge cannula directly into dense submucosal tissue?
It sounds hyperspecific, I know, but this scenario is basically the ultimate crucible for medical engineering, and it's happening thousands of times a day globally.
Yeah.
So to truly grasp the friction in the system, we have to look at how three distinct elements collide. You've got the payload being injected, the microscopic delivery vehicle, and the target environment, which is the aggressively hostile human face.
Okay, let's unpack this because we have to start with that payload. If you've ever dealt with these high-density fillers, you know we aren't just squirting saline here. Far from it. Yeah, I was reading through the rheological data on these gels, and they keep emphasizing this metric called G prime, or the elastic modulus. Now, I understand that a high G prime basically means a stiffer gel.
Right, exactly.
But I'm struggling with the manufacturing side of it. Like, how do you engineer a liquid to act like a solid structural pillar once it's actually inside the body?
Well, it is a massive chemical balancing act. You are trying to create a material that can flow through a tiny tube when it's subjected to extreme pressure. But the absolute second that pressure stops, it has to lock into place.
And it has to resist deformation.
Exactly. If you think about the clinical application, practitioners are placing these high G prime fillers along the jawline or the midface.
Right, which are areas that move constantly. I mean, you smile, you chew, you talk.
Yeah, your facial muscles are constantly contracting against the skin. So if you put a low G prime filler there, something with the consistency of like a soft pudding under a heavy muscle, the sheer mechanical force of you chewing your food over a few weeks will just squish that filler flat.
You would just migrate everywhere.
Right. It loses its projection. A high G prime filler has to fight back against those facial muscles. It has to act more like a firm jello block that holds its shape and physically props the tissue up.
But the sources also talk about the risk of fragmentation. So if a gel is too stiff, wouldn't it just crack under that muscular pressure? Like stepping on a dry sponge versus a wet one?
Yeah, and that is the exact problem manufacturers have to solve with cross-linking. You can't just make the gel thick, you have to make it highly cohesive.
Meaning the particles have to desperately want to stick together.
Precisely. Take the VYCRS technology mentioned in the studies. They don't just use one single type of hyaluronic acid molecule. They actually blend long, high molecular weight chains with short, low molecular weight chains.
Oh, I see. So the small chains are essentially acting as mortar between the larger bricks.
That's a great way to put it. The low-weight molecules fill the microscopic gaps between the large chains, which creates this incredibly dense, tangled network.
Wow.
And then there's the oxide-free technology, which attacks a totally different problem. It deals with oxygen degradation during the manufacturing process.
Yeah, I read the oxide-free part, but I honestly didn't buy the premise at first.
Yeah.
I mean, how does extracting ambient oxygen during manufacturing actually change the physical strength of the filler once it's sitting in someone's jaw?
Well, it really comes down to protecting the structural integrity of those hyaluronic acid chains before they ever even leave the factory.
Okay, how so?
Free oxygen radicals in the manufacturing environment actively attack and break the long polymer chains of the hyaluronic acid. Think of these chains like long, tightly coiled springs.
Oh, and if oxygen radicals snip those springs in half, they lose all their tension.
Exactly. So by removing the oxygen during cross-linking, oxy-free preserves those massive chains perfectly. The result is a gel with just an immense capacity to project tissue upward and hold it there.
Okay, so we have engineered this perfect, cohesive, concrete-like gel to lift the face. But that creates an immediate physical nightmare for the doctor.
Oh, absolutely.
Because how do you force concrete through a straw? Which brings us to the delivery vehicle. And I have to push back on the clinical logic here based on the physics.
Okay, let's look at the fluid dynamics.
Right, because if we have a thick, stubborn payload that actively resists flowing, utilizing a microscopic 27-gauge instrument seems like a terrible idea. From a purely mechanical standpoint, why not just use a much wider needle? You'd completely eliminate the extrusion force problem.
What's fascinating here is that if we were injecting into a vacuum, yes, you just use a garden hose. But we are navigating the highly vascular anatomy of a living human face. Patient safety completely overrides fluid dynamics.
Right, because using a large bore needle to push a highly viscous gel into the face is incredibly traumatic.
Exactly. Because a sharp needle acts like an ice pick. It cuts indiscriminately.
And if a large sharp needle encounters a blood vessel,
It slices right through it. And that leads to severe bruising or, far worse, vascular occlusion. That's where you accidentally inject that thick, concrete-like gel directly into the artery, blocking blood flow entirely, which is a catastrophic complication.
which is why the clinical guidelines in the sources mandate the 27-gauge blunt microcannula.
Yes, the blunt tip changes the mechanical interaction with the tissue completely. Instead of an ice pick, think of a rounded snowplow.
Oh, that makes sense.
As the cannula moves through the facial planes of the face, it gently pushes blood vessels and nerves out of the way rather than slicing them. And because it's flexible, a practitioner can make one tiny entry point and fan the cannula out to treat a really broad area.
It's fantastic for the patient. But physics demands a toll. By shrinking the delivery vehicle to a 27-gauge tube, you are severely punishing the person holding the syringe. I mean, the flow resistance must be astronomical.
It really is. If you look at the principles of fluid dynamics, specifically Poiseuille's law, which governs how fluid moves through a pipe, the resistance doesn't just increase a little bit when you make the tube smaller, it increases exponentially.
Is it based on the radius to the fourth power?
Yes. If you cut the radius of a tube in half, the resistance to flow doesn't just double, it goes up by a factor of 16.
Wow.
So trying to push a high viscosity, high G prime gel through the microscopic internal diameter of a standard 27-gauge needle requires a level of force that basically borders on impossible for a human hand to sustain.
So how is it happening? I mean, I know they are doing it every day. The math says it shouldn't work. So how are they cheating the physics?
While they alter the geometry of the tube itself using ultra-thin wall technology. The research highlights TS-keyed technology as a prime example of this.
Oh, I saw that.
Yeah, the biomedical engineers recognized that they couldn't change the outside diameter of the cannula. It has to remain a 27 gauge to protect the blood vessels. But they realized they could shave down the metal walls of the cannula from the inside.
So by making the metal barrel thinner, they steal back internal volume.
Exactly. They maximize the internal real estate, and the numbers are incredible. By utilizing ultra-thin walls, they increase the internal diameter by up to 65% compared to a standard 27-gauge needle.
Wait, 65%? That isn't just a marginal improvement. That is a massive expansion of the flow channel.
It completely alters the resistance equation. I mean, without that 65% increase in internal volume, the pressure required to push the gel would likely blow the syringe apart.
That's wild.
But even with that brilliant engineering sheet, the fluid dynamics are only half the battle, because the tube eventually ends and the gel has to enter the tissue.
Right. And injecting this filler isn't like squirting water into an empty glass. The target environment is hostile. You are trying to inflate a space that actively does not want to be inflated. It's like inflating a balloon buried under dense rubber.
If we connect this to the bigger picture, we really have to analyze the submucosal and subcutaneous layers, because these aren't empty voids. They are tightly packed, highly pressurized environments.
Right, constructed of dense collagen frameworks embedded in mucopolysaccharide gels.
Exactly. They are structural shock absorbers. They are built to hold the face tightly together and resist expansion, which introduces the concept of tissue counterpressure.
Because when you push fluid into this space, the tissue fights back back with an equal and opposite force.
Yes.
And the data from the fluid injection models in our sources is absolutely wild regarding this counterpressure. I noticed that the volume of fluid you inject actually matters way less than the speed at which you inject it.
The injection rate is the critical variable here.
Because in the swine model studies, they show that if you try to rapidly inject just 1 milliliter of fluid, let's say over 10 seconds, the tissue back pressure spikes to an enormous 24.0 kilopascals.
Right.
But if you take 10 times that volume, so 10 milliliters, and inject it agonizingly slowly over 10 minutes, the pressure only reaches 7.4 kilopascals. I mean, I understand the data, but what is the actual physical mechanism causing that huge discrepancy?
It's a phenomenon called viscoelastic creep. Think about a material like silly putty. If you grab silly putty and pull it apart very slowly, the molecular bonds have time to stretch and accommodate the movement. You can stretch it for miles.
Right, but if you yank it violently, the bonds don't have time to adapt, and it just snaps in half like a solid piece of plastic.
Precisely. And the tissue acts the exact same way. The collagen framework in the face is viscoelastic. When you inject fluid very slowly, those collagen fibers have time to stretch, separate, and accommodate the new volume.
So the counterpressure stays relatively low.
Right. But when you try to forcefully push fluid in rapidly, the fibers lock up. The tissue essentially turns into a rigid concrete wall, causing the counterpressure to skyrocket to that 24 kilopascals mark you mentioned.
And we see a brilliant demonstration of just how rigid that wall can be in the water jet injection studies.
Oh, those studies are fascinating. They were attempting to inject particles into mucosal tissue using high-velocity, needle-free water jets.
And the tissue basically acted like a trampoline, right?
Yeah, it repelled the fluid entirely at lower pressures. They mapped out specific pressure profiles, and if they fired the water jet at an E5 or E20 pressure profile, the fluid literally bounced off the submucosal tissue.
Just failed to penetrate.
Completely. They had to crank the velocity up to massive E40 and E60 pressure profiles just to forcefully breach the tissue matrix and distribute the fluid without blasting completely through to the other side.
If it takes a high-velocity, weaponized water jet just to penetrate this tissue layer, it really frames the absurdity of what a human thumb is trying to accomplish with a little plastic syringe.
It really does, which brings all the variables together. We have a highly cohesive, thick payload. We are forcing it through a 27-gauge tube that, even with ultra-thin walls, heavily restricts flow.
Yeah.
And we are pushing it into a dense collagen matrix that violently resists rapid expansion.
So what does this all mean? Like, what is the final mathematical toll on the human hand? This is the part of the data that actually made me stop and reread the page. Let's look at the raw extrusion force numbers, and we have to start before the gel even touches the patient.
Okay, yeah.
I was looking at the York-based research on syringe ergonomics, and they noted that simply moving the plunger of a completely empty syringe, just pushing air, requires between 5 and 16 newtons of force.
Which sounds counterintuitive until you look at the mechanics of the syringe itself.
Yeah.
To prevent the high-pressure fluid from leaking backwards out of the barrel, you need a perfectly airtight seal.
Right.
So you have an oversized rubber stopper on the plunger that is being violently compressed inside a rigid plastic or glass barrel.
So you are fighting the viscoelastic friction of rubber dragging against plastic before you even begin the procedure.
That baseline drag is significant. Now factor in the rest of the system. You load that syringe with a highly viscous, high G prime submucosal agent, attach the restrictive 27-gauge microcannula, and attempt to displace dense facial tissue.
The patent data for these submucosal compositions states that the required injection pressure jumps to a range of 2.5 to 4 kilogram force. So, converting that for consistency, the practitioner has to generate roughly 24.5 to 39 newtons of continuous force.
39 newtons?
Yeah. To make that tactile for you, imagine holding a 4-kilogram dumbbell that's almost 9 pounds. Now take that entire weight and try to balance it solely on the pad of your thumb.
It's crazy.
That is the physical load the practitioner's thumb has to support continuously just to keep the filler moving through the cannula.
And that biomechanical reality crashes right into the limits of human anatomy.
Oh, the ergonomics studies outline this perfectly. They suggest that for a practitioner to maintain comfort, steady fine motor control, and precise depth perception, the maximum acceptable injection force is 40 newtons, and ideally you want it under 20 newtons.
But the math dictates that the required force can easily plateau at 39 newtons. Practitioners are routinely operating right at the absolute red line of human capability.
Now, I know the average maximum thumb force for humans is higher than that. The data shows males average around 95 newtons and females around 64 newtons. So technically, they have the raw strength to push the plunger.
Sure, but raw strength is totally irrelevant when you introduce fatigue and precision. You are relying primarily on the abductor pollicis brevis muscle in the thumb, while simultaneously using your index and middle fingers to pull back on the syringe flanges.
It's a complex isometric hold.
Exactly. If a practitioner is doing 10 of these procedures in a day, pushing against 39 newtons of resistance each time, that muscle exhausts rapidly.
And when a muscle exhausts under an isometric load, you don't just lose strength, right? You get tremors. You lose the micro-precision required to place the gel safely.
Which is incredibly dangerous when you are millimeters away from major facial arteries.
But let's say the practitioner is determined. They hit a particularly dense pocket of collagen, the tissue counterpressure spikes because they're pushing too fast, and they decide to just muscle through it. They squeeze with everything they have.
Here's where it gets really interesting. This is where the physics of incompressible fluids takes over. If the fluid cannot move forward through the cannula fast enough to relieve the pressure, and the tissue is acting like a concrete wall, that massive buildup of kinetic energy has to go somewhere.
It finds the absolute weakest structural point in the entire system.
The connection between the syringe and the cannula.
Yes, the Luer lock hub. The sources document this failure cascade perfectly. If the extrusion force exceeds the structural integrity of the plastic threads, the overwhelming back pressure causes the cannula hub to literally explode off the end of the syringe.
A catastrophic blowout. Yeah, the fluid essentially breaks the tool because the physical parameters were pushed way beyond the breaking point of the materials.
It completely reframes how I will view these procedures moving forward. You aren't just watching an aesthetic touch-up. You are watching an intense, continuous negotiation with fluid dynamics and biomechanics.
Truly.
Every millimeter of movement is a practitioner harmonizing the complex cross-linked rheology of the payload, relying heavily on the ultra-thin wall geometry of their cannula, and riding the razor's edge of their own physical thumb strength, all while actively battling the structural resistance of a living, dense collagen matrix.
It is a remarkable feat of human skill leveraging brilliant engineering, but when you look at the trajectory of the data we've discussed today, it inevitably forces a much larger, frankly provocative question about the future of this field.
Because the variables are moving in opposite directions, right?
Exactly. Look at the demands of modern aesthetic medicine. The clinical trend is pushing for even thicker, higher G prime, longer-lasting fillers to achieve dramatic facial lifting. At the exact same time, patient demand is pushing for even thinner, smaller cannulas to guarantee absolutely painless, bruise-free experiences.
So the payload is becoming thicker and more stubborn, the delivery tube is becoming narrower, and the tissue resistance remains a constant. The math says the extrusion force is only going to climb.
It has to. We are already riding the absolute red line of that 40 Newton limit for human comfort and control. If these materials advance even slightly further down this path, the required force will exceed what the human thumb can safely and precisely deliver.
Wow.
So the question becomes, will the future of aesthetics be forced to abandon the traditional hand-powered syringe entirely? Will practitioners have to rely on motorized, automated, or even robotic injection devices to push the plunger simply because we have engineered ourselves right past the absolute physical limits of human anatomy?
If the gels get any thicker, the human hand won't just be the bottleneck. It will be the point of failure. We started this deep dive thinking about a simple plumbing problem, but the physics dictate that the future of cosmetics might actually require robotics. It's an incredible concept to grapple with. Keep questioning the hidden mechanics behind everyday medical marvels.